Let's now consider force systems that have a non-zero net resultant moment. So these are force systems that are no longer concurrent. So just to remind ourselves, so the total resultant force is just simply the sum of all the individual forces, and the net resultant moment about some arbitrary reference point, which I've labeled 0 here, is just simply the sum of the moments of the individual forces relative to that reference point, which I've labeled O, as I've mentioned here. So let's go ahead and look at an example to see how this works out. So let me consider a rectangular object, 5 meters by 10 meters, that's subjected to a 10 Newton force in the x direction. And let's go ahead and look at a characterization of this force system relative to the 2 points A and B. So let's start with B. So if we start with B, I'm going to be setting the reference to B. The net resultant force R here is just simply the sum of all the forces, so that's just simply 10 newtons in the x direction. And then the net resultant moment relative to point B is going to be equal to 0. And the reason for that is that the position vector from my reference point to the point of application of the force is just simply 0, and 0 cross any vector is always equal to 0. So that gives me a net resultant moment of 0. So that's the characterization of this force system relative to the point B. Now we can also characterize the force system relative to the point A. In that case, the net resultant force is going to be the same. It's 10 newtons in the x direction. But the net resultant moment relative to A is different now. So it's the position vector from A to B crossed with the force in B, and that gives me minus 50 newton meters about the z-axis. So pictorially I can draw it as shown here. I can put the force here at A, and I can put the negative 50 newton meter moment here at A also. So that's just simply a different characterization of the force. Both of these force systems are, as represented here and as represented here, have the same net effect on the body here, assuming that it's rigid. Important remarks to keep in mind here. One is the characterization of a force system in terms of resultants depends in general on the reference point. So we've seen that if I pick point A or if I pick point B, I get two different representations of the force system. They still provide the same response of the body if I do further analysis, but I have two different results, and one can be easier to use than another in given situations. The other one to note is a special fact of that last problem is that I had all the forces lying in a single plane, in that case the xy plane. And when you have the forces laying in a single plane, then the moment, the resultant moment associated with that system of forces will always have a single component, and that component will be orthogonal to the plane of the forces. So in the case of the example that I did, the forces were in the xy plane, and so they had a single component in the z direction.